Good morning, good afternoon, and good evening, everyone. So today we're going to be finding roots. And here in our scientific computing course, we're going to be looking at different methods to find roots. So again, what are roots? So roots are, let's say, for instance, we have, okay, before we get into this nitty gritty stuff, so roots are basically when we have, let's say, some plane, right? The XY plane. And let's say we have a curve. Well, our roots are basically solutions. So when we say roots, we mean x-intercepts. Those are solutions, right? That's basically what we mean. So roots are basically when we have some x, our f of x is 0, some x, and our output is 0, right? That's basically what roots are, right? Okay, so let's just hop right into it, yeah? Okay, sorry about that. So here we have different methods for finding roots, and I'm just gonna go over some of them, brief review, right? And now I think my thing lagged. Okay. So one of the first methods that we encountered was this idea of bisection method. Now what again is a bisection method? What in the world is that? Bisect. So here, let's say we have 2 points. We have XL, XR. Let's say that's 1 and 2. I don't know. Let's say that's 1 and 2. 1 and 2. And so we're going to make a center guess. And our center guess is going to be our 2 points when we add them together and we divide it by 2. 1 plus 2 divided by 2, 3 halves, or 1.5, right? So that's our XC, X sub C, which means that's our center, 3 halves, right? 1.5, the middle, right? We're basically getting the middle. That's what we're doing here. And then we look at the sign of our function of X of C again, and then we determine which point XL and XR it differs. Now, what in the world do we mean by it differs? Well, we mean that if our f of x sub c, so in this case our 1.5 XL, so our f of 1 have different signs. So let's say one of them is positive. I'm talking about the outputs, right? So one of them is positive, one of them is negative, then the root lies in that particular interval. But if they have the same sign, then most likely it lies here in this interval, 1.5 and 2. And then from there, we keep doing the same thing. So what do we mean by do the same thing? Again, we make the center guess. So 1.5 plus 2 divided by 2, we get our center again. And then we do these set of steps again. So that's the whole idea of the bisection method until we find a solution. Okay, let's do a quick example, yeah? So let's do some example of this. I think I'll do it in code, but we'll see. So here's our exercise. I'm going to go ahead and try one of these exercises. So okay, let me just hold on. I'm actually asking ChatGPT for me to do this. Okay, let's do this. Okay, so you have a couple of them and some application stuff. Ooh, applications are really cool. I'm not gonna go into the applications just yet. Okay, let's go to number one. I'm just making GPT do this. So here's the problem, right? We want to find the root of such a function, f of x, and f of x is equal to x cubed minus 4x minus 9. Specifically on this interval, 2 to 3. Now, how in the world do we do this analytically? So analytically, this is hard, right? This is hard because there's no way to factor it out or anything. It's not quadratic. It's actually a cubic function. So one way we can do this, I guess, is through intuition. So here's what I'm going to do. I'm going to go ahead and share my screen here. I'm going to go to Desmos and find the roots myself, specifically at that interval. So let me go ahead and just do this. Y equals x cubed minus, I think it was 4x minus 9. Yes. Now it wants me to find a root here at 2/3. Here we found it. Oh, it's like 2.70653. So that's a very long number, definitely not analytic. That's a number approximation, right? So how in the world do we do this using our bisection method? So maybe that's one thing we want to think of doing, right? So let me go back here. I'm going to first try to do this manually. So here we say, okay, so that's my function, right? I plug in f of 2 here. Or actually, I find my center. Let me find my center. X sub c is 2 plus 3 divided by 2. Right? That's 5 halves. And then I think that was, I don't know, not good at calculating. 2.5. Anyway, I should have just known because it's 2 and then 2.5 is in the middle. Okay, so that's my thing there. If I plug in a 2 in my function here, I get 2 cubed minus 8 minus 9. I get negative 9, right? And then if I plug in f of 3, well, I get 3 cubed, that's 27, minus 12, minus 9, that's 6, right? And then I plug in my f of 2.5. Okay, and this would give me around, like what? 2.5? I don't know, let me compute it myself. Like 15.625 minus 10 minus 9? Minus 10 minus 9. Oh, not 10. What am I doing? Oh, it is 10. 2.5 times 4 is 10. 2.5 cubed is 15.625 minus 10 minus 9. So yes, it's around 3.375-ish. And then here we see that, okay, which one has the differing sign? Here, these two, right? They have differing signs, so it means we have to look at this interval now. We find the middle, then we keep looking at this interval, right? Okay, the computation in GPT is wrong, but cool. Okay, so we found that, right? Okay, let me go ahead. So yeah, the root should lie somewhere in 2.5 and 3. Now, based on our Desmos graph, it does, right? Because it's like 2.70653-ish. So if we keep going, so we get our center here. That's 2.5 plus 3 divided by 2. That gives me 5.5 divided by 2. That gives me around, like what, 2.75-ish? So that's my center, right? And then I plug in the stuff I need. So I already have 2.5 and 3. So no need to worry about that part. So I have that number. Now I need f of 2.75, which should give me, so if I just plug in 2.75 for everything, I get, oh, what in the world was this, like 20.79687.5 minus something? 4 times that number? Oh, it's 11. That's nice. Then minus 9. 20.796875 minus 11 minus 9. Okay, gives me around like 0.796875. Gives me that number. Now, which one has a differing sign? These two. So that means the root lies in between 2.5 and 2.75. And if I check my Desmos, it does, right? My Desmos says it's 2.70 something-ish. And so I keep going, right? So this is why it needs a computer now, because I need to keep on going until I find the root. So let me go ahead and switch to a computer to do this, specifically in Python. I'm going to do this in Python. So here's what we're going to do. I'm going to open a new thing here. New window. I'm going to go ahead and share that window. I'm going to go to CodePad and I'm going to graph this out. Or do this root finding algorithm here. I'm going to code it up. And I'll show you guys that for every iteration, we're going to see, oh, it does converge to a root. So that's something we're going to look at. Okay. So how do we do this, first of all? Well, first, we kind of want to define the function, right? So we want to define the function here. Okay, let me go ahead and do this. So I'm going to define the function. It's going to be called bisection because that's what the method is. So bisection method. I go from f, a, b, right? My ab is my 2 points. Then maybe just add a tolerance just in case. I'm adding the tolerance in case it doesn't converge to a root. That's what a computer is for. Let's say there is no root. It will go somewhere close to a root, right? So we need to have that value. Yeah, also, we cannot get this analytically. This is a numeric solution. So if f of a, here we're going to do the conditions, right? If f of a, if we multiply that to b, is less than 0. So meaning they have different signs. If we multiply a negative by a positive, then it should be a negative. So let's say if it's negative, or actually, oh my bad. If it's greater than 0, then there is no interval, right? I'm going to do a value error here. There is no interval. Or no solution, or something like that. No root and interval, right? Because it has to be in the differing sign. Okay, then I'm going to do a while loop here. So while my b minus a divided by 2 is greater than my tolerance, right? Then I'm going to get its center. So here a plus b divided by 2. That's my center. Then let's say it's equal to 0. If my f of c, this is a root. But in the instance that my output is 0, then I just return that because that's my root. Right? elif, so here else if, in Python it's elif. Elif, else, elif. Else if my f of a times f of c, or my center, right, is less than 0, what happens? So this is when my f of a, so my first point, when I multiply it here, it has differing signs because it's less than. So if it has differing signs, then I assign b to c. So that's my new b. So now I'm going to go and check the interval. Then from there, oh yeah, else, let's say it's greater than, or it's another case, then my a is assigned to c. And from there, I just return, oops, I think it was here. Oh yeah, I just return this a plus b divided by b, right? Okay, yeah, so that's my root. That's it, right? Now let's try to actually do an example. The thing that we did, I'm gonna do a lambda. This one's gonna help me write out the function here. Lambda's kind of like an anonymous function in a way. Here's what's nice about this thing though. I can just write it like normal, like this. I think it was minus 4x minus 9. There we go. So that's my function, right? X cubed minus 4x minus 9. Yeah. And then from there, I'm going to do a root bisection. So I'm going to do the bisection method I did. And here I'm going to input my function f, my a, my b. So in this case, it's 2 and 3, right? I think it was 2 and 3. Yeah. So it's 2 and 3. And then tolerance is optional. I have it by default, so I don't need to put it there. And I just print out my bisection root. Right? That's like around something-ish. So around, I don't know, around like there. If we do print this out, and there we have it. Around 2.71 based on this algorithm. So it's not exactly as the one like in Desmos, but it is a solution, right? Okay. Maybe let me, okay, here's what I want to do next. I want to show you guys how it looks like when, oops. Uh-oh. Okay. So what I'm gonna do is print out each iteration step. Okay. Uh-huh. Oh, go ahead and do it for this. Wait a minute. I'm just asking GPT to do this for me. 'Cause I don't wanna. Okay. Cool. So let me go ahead and just copy this, paste it here. And there we have it. If I were to look at it here, oh, that's a nice looking graph. So at my 0th iteration, this is my root, my interval 2 and 3, the middle, C, center, and then sort of my function. And then I keep on going. After 5 iterations, I should get, or I should converge to some solution 2.71, right? So that's the solution numerically. So that's basically how this kind of works. And so if we don't have like a decimals, for instance, or if we want to numerically compute something, then we might as well use code to do it and use these methods, right? Okay, let me try a different one. Let me go back to my sharing. So that's the idea. So if we keep going, we get to some solution. So we get to root of, I think about was 2.71-ish. Okay, that's the bisection method. I hope that makes sense. Okay, moving on. Let's go ahead and do a Newton-Raphson method. So just a brief review. Newton-Raphson method is basically this. We linearize a function. What do we mean by linearize a function? Let's say we have some function. Okay. Let me do exercise Newton-Raphson method. So here's what we mean by we linearize the function. Let's say we have this xy plane. We have some curve like that. And let's say this is some point x sub 1. Or actually, zoot a. That's some point a. And then the output of this is f of a. And here we want to, so we call this f of x. And so if we want to linearize this function, we want to get the line at that particular point. That's what we're doing. So if we're getting the line at that particular point, well, then we want its point exactly there, right? So the line at that particular point, so that's f of some x value. So in this case, f of a. So we want that. We want to add it to its derivative. So if we get the derivative, we'll actually get something like this. Oh yeah, wait. If we get the derivative, we'll get some tangent line. And then, or we get the slope of that tangent line. And then we do x minus a. Right? So instead of, I think I did like x minus x naught, right? Yeah, x minus x naught. Instead of x naught, I do a. Yes. And then this blue line here, the equation of that line is just L of x. And then we keep going. And then that's how we can approximate L at a specific curve here based off of a. So if our a was here, then we could get something like this. So it's kind of like a linear approximation thing, right? So that's Newton. So we start off with that. We linearize our function at a particular point. And then from there, after we linearize, so let's say we have x naught. So we just, let's say it's not a, let's say it's x naught. So initial point. From there, we find the root. So what happened? Well, we basically set this to be equal to 0. And so this is my L of x. We set it to 0. We solve for it. So just some simple algebra here. And we get this. So this is my x, and then my initial point. And then we can use our Jacobian iteration scheme. So we can actually iterate. So instead of x naught and x, we can say this is the following point. This one's the current point. So here we're saying xj is the current point. Xj plus 1 is the following point, the next point. So that's our way of iterating. And then we do that again and again, provided that our derivative here, or f of x, f prime, shouldn't be 0 or else it would be undefined. As simple as that. And that's what we know as the Newton-Raphson method. And we can use this if we know what f prime is. Okay, let's actually try this in practice. And I don't think I can do this through an exercise or through the... Anyway, we'll try. So let's say we want to find the root of this function. So again, what these methods are is about finding roots. We want to find the root specifically of f of x. Cosine, so it's a trig function, minus x. And here, we make our initial guess. So we make our initial guess, let's say x naught. So that's x naught, right? X naught is going to be, I don't know, 0.5. Could be something else. Could be 5, could be 100, could be a million. Could be 0.5, could be 0. Doesn't matter. And let's say we're going to stop until we reach our tolerance of 10 to the, I think it was -5. Yeah. So we could do this manually, right? Where we use this, not secant method, we use this xj plus 1, xj minus f of xj, f prime of xj. We can do that, but I'm not going to do that. What I'm going to do, I'm going to do this in code. Because it's annoying. Okay, let's do this in code. But I'm basically going to use the Newton-Raphson method, right? Okay, let me go ahead and do that. So here I'm going to import a library called math just to make my life easier. And I'm going to define the Newton method. I'm just going to call it Newton, doesn't matter. You can call it anything. Encoding, you can do that. Here we're going to, in our Newton-Raphson method, we need our function, its derivative. So I'll just do df. We need our initial point. We need our tolerance of, I think it was by default, 10 to the -5. So I'm going to do like 10 or 1 e minus 5. Then I think something else. Let's say max iterations. Let's consider that in case we don't converge to a solution. Because sometimes we won't. That's the thing. Sometimes we won't. We'll just get close to some solution. Let's do a for loop here. Range iter. So that's the number of iterations we're going to use. And we're going to use our Newton-Raphson method. So x1, the following point is going to be x0 minus our function. So our function at f of x divided by its derivative at the same point, right? And then what are we going to do? Let's say we get its absolute value, right? Let's say its absolute value of x1 is less than the tolerance that we have. Let me do this. Then we just return x1. Just return the following point. The moment that we see it's less than the tolerance, which means we can now fit in. We can say that, okay, that's a good enough solution as we've reached our tolerance. Because it's only going to get closer and closer and closer until we reach such a tolerance that we can assume that, okay, we've found the root. Or else, yeah, so here's the case. Or else, in case we didn't run into a solution, then we're just going to raise some error here. Raise runtime error. Wait a minute. Yes, so during runtime, well, we did not converge. Okay. And I do so now I apply it, right? Here I do my lambda. And I think this was x. Here's where I use my math, because there's no such thing as cosine in programming. In MATLAB, I think there is. You can just by default type it in. So that's what's good about other programming languages, is you can just type it in and there's a default for it. Here in this case in Python, there isn't, unfortunately. And if we get the derivative, well, I don't really need to like go depth into it. But if we get the derivative, we get negative sign. So that's calculus -1, I think. Yeah, because derivative of x is 1. And then there we go. We just get the root using Newton method. So here the code does it for us. And so we plug in our function. And then our initial point was, I think we started with 0.5. And then we just print the root. Okay. This one should give me the root around that point. So if we run it, and there we have it. 0.739-ish. And then if I check it in MATLAB, in Desmos, should converge to that. But then again, we're not super sure because we added tolerance. What's my function again? It wants me to, I want to find the root of y cosine x minus x. Specifically, oh, so one solution is this one. Yeah, like 0.73909. 0.7390. So this is more precise. Here we can see this is more precise. Now, analytically, if we want to get the exact value, then we have to solve for it. And I think solving for it might be, is it possible? Let me try actually. But the numeric solution gives us a more exact solution. No, not exact, more precise. Let's see this. Can I solve for this analytically? Like just using methods that we know. So, okay. I'll set it to 0. We got this value. What's cosine of something which is equal to something? What's that? Cosine 0, cosine 1. I don't think that, does this exist? What is that value? I'm a bit curious myself. Let's do it is there a way? Oh, so it cannot be solved. Or wait, decreases, blah blah blah. Yeah. Okay, so it cannot be solved because I'm thinking of like, okay, what if we do plug in one or something? Plug in zero. So this thing is again unsolvable. So these are also one of the reasons why we want to use numeric methods because they cannot be solved like analytically, like this way. So again, cannot be solved algebraically, analytically. These are what we call analytically because we're finding exact solutions, right? Sad face. But we did find, so through code, we were able to find the root more precisely compared to Desmos. So using Newton-Raphson, root, or it converges to around like 0 point. It was a very big number too. It was like, what? You're gonna write it out. I forgot. Where did I put my code? Oh, there. Like 0.73908 something, right? So it's actually more precise compared to Desmos. So that's the idea of using these methods. They give us more precise solutions. Okay. Fun fact, they call it a Dotty number. Apparently, that's called a Dotty number. If we do like cosine x is equal to itself. That's weird. Okay. Anyways, let me go ahead and do this. Okay. So what else can we do? Yeah, so that's my Newton-Raphson, pretty much. And lastly, let's do secant method. And then we'll call it a day. So lastly, for secant method, here's what secant method is. So most of the time I'm doing this in code. I'm not doing it in handwritten. You can, but it's very, very, very tedious. So for secant method, it's basically a modification or what we call more flexible Newton method, right? If this was the Newton method, and let's say, or let's get the definition, the limit definition of a derivative. And what is that? It's basically this, right? That's the limit definition. So this is from calculus 1, calc 1. And what this is saying is that as that limit goes to that particular point, our slope is approaching that point. So what if, let's say, we don't have that? We don't have the derivative. Then that's where the secant method comes in, right? So here, this is actually, so the limit of this thing is actually just approximately the slope itself. Again, approximate, not exact. So instead of finding a tangent, we're actually just using the secant, which is the approximate thing, right? So we get this thing. And then from there, we're going to use this instead of the derivative. And so we get something like this, right? So here, we actually have 3 points. We have the following point or the next point. We have the current point, and we have the previous point from that current xj. So we have j plus 1, j, and j minus 1. Now we have 3 things to consider. right? And this is useful if we don't have the derivative. Okay, let's do an example. And yeah, provided that this j minus 1 is not equal to this, or else it would be 0. As simple as that. Okay, let's go ahead and do an example here. Let me... Okay. Let's find root. So again, these are root finding algorithms or methods. Here we have some function f of x. This is ln of x. We're going to add it. And then this one is, so we have our initial point, x naught is 0.1. And then we have our x sub 1 is, I think this was 1.0. Okay. Go ahead and do the secant method. Actually, let me, I'm just gonna show you guys what this looks like in code, because I really don't want to do this manually. That's what applied math is for. We want to put in code instead of doing it manually. And I kind of prefer it that way. Anyway, so here, let me, or actually from intuition, what do you guys think is gonna happen? Will there be a root? What do you guys think? Will it converge to a root? I don't think so. Based on my experience with natural logs, I don't think it does. We'll see. What does ln of x look? Ln, does that look like? Am I trying the right thing? Okay. What does that look like? Well, let me see. Ln x plus x. Yeah, let's try. Oh, has a root. 0.56714. Or actually, nah, I psyched myself. There's a root. I was thinking of the y-axis. So it's there. 0. Somewhere there, 0.56714. That's obviously not exact, right? It's a numeric solution again. And so here we defined it, right? We defined the secant method. Our max iterations is 100. We have a tolerance of 10 to the negative 5. We did that for loop. And here's our equation, right? So we have the x1 minus f of 1, x1, x0, x2. So we have x2, x1, x0. x1 being our current point, x2 being the next point, x0 being the previous point. Again, we get the absolute values, we equate them, raise our runtime error, and then here's our application. So we do ln of x plus x. Secant from, we have this info. X naught is 0.1, and x to the 1 is 1. And then we have a root secant. So if we run this, we should get, there we go, 0.56714, blah, 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 which is this one. But that's a more precise way of getting it, right? So again, I think personally that's what's important about finding roots. It's that we cannot always rely on analytical solutions to find these roots or to find these solutions. Sometimes we have to get approximate ones, and we can get the better and better approximations using numerical methods such as these three. So here, just a brief recap. What we discussed was we discussed three methods for root finding, and those are what we call the bisection method, the Newton-Raphson method, and the secant method. And yeah, I'm not gonna. So yeah, root approximately is around like what, 0. I'm not gonna write everything. It's like, and I was sharing the wrong screen. So root was approximately, what was this? 0.5671. 567. I was gonna write that. Ish. Yeah. Anyway. So yeah, those are some interesting stuff about applied math and scientific computing. It's that we can find approximations of roots, since sometimes, or in most cases, if we're working with real world data, we cannot find exact roots using analytical techniques, right? Like setting y to 0 and then solving it algebraically using algebra. sometimes you have to rely on these numerical methods to find these solutions. So yeah, I hope you guys had fun. I hope you guys enjoyed this video. I hope you guys learned a lot, and I'll see you all in the next one.